What's up? I'm Vin, and today I want to go through the August 2022 Geometry Regents, and I'm doing parts 2, 3, and 4. So let's start with question 25. We got triangle dog congruent to triangle cat, and we want to describe a sequence of transformations that will map triangle dog onto triangle cat. So the first thing that I look for is the pair of sides that are the same. So GO definitely matches up here with TA. And the way that I know, I could use the distance formula, but that would take forever. These just look the same, but if I really want to be safe, just count the rise over run. So here I'm rising 1, 2 and going over 1. And over here I'm going down 2 over 1, but since the units that I'm rising and running by match, these two are going to be the same. And now notice here that this kind of looks like a right angle, and this right angle leads to side DG, and this right angle leads to side TC. So that tells me that those two are the same, but I could use that rise over run again. I'm going down 1 over 1, 2, 3, and over here I'm going up 1 over 1, 2, 3. So those two are definitely the same, and then these sides are going to match up. Now, what I look for next is if the orientation is the same. Notice this one, if I go clockwise, I get from the single to double to the triple notch. Whereas in the next triangle, I would have to go counterclockwise to get from the single to the double to the triple notch, which tells me that a reflection was done. So that means I'm going to reflect first. And what I have here is I could reflect over the y-axis. So to reflect, I'm going to count the distance to the y-axis. So I go over 1. So then I have to go that exact distance across the line of reflection. And I'll call this O prime. And now at this point, I'm going to count 1, 2. And now I'm going to go 1, 2 past the line of reflection to G prime. And now this last point, I'm going 1, 2, 3, 4, 5. So I'm going to go 1, 2, 3, 4, 5. And this would be D prime. But now I just have to think, how do I get this triangle here, this kind of midway triangle, to go from here to triangle cat? Well, now I just count the vertical jump. I'm going up 1, 2, 3, 4, 5. So now we did a reflection over the y-axis, and now we're doing a translation to the right 0 units, but up 5 units. Now, just to double check that we're correct, I'm going to translate these points too. We go up 1, 2, 3, 4, 5, and that matches us up here. And now if we count 1, 2, 3, 4, 5, that would map G prime onto T. Question 26, we've got this right triangle, and we need to determine to the nearest tenth the volume of the 3D solid formed by rotating this triangle continuously around side MH. So for these questions, you have to be good at seeing things spin. And we're spinning around MH, and the thing we're spinning is a right triangle. So if we were to spin it in a circular motion, that's going to make a cone. So I'll just go ahead and draw a cone over here. So we have this nice cone over here, and we'll just make it look 3D like this. And I'll go ahead and draw this triangle on the inside. So up here would be M, and H would go down to the center like this. And then T would extend out like this to any point. But just imagine that this thing is like continuously spinning here. So this is just spinning in circles to form this cone. Well, one thing to be mindful of is that HT is 8 units long. That represents the radius of this cone, and the height is going to be 5. I know I didn't draw this to scale, but this is just to help us visualize what's actually happening here. So now that we have the height of this thing is 5 and the radius is 8, to find the volume of this cone, we would use 1/3 pi r squared h. Now, one thing that throws students off is they'll mix up which one is r and which one is h. But just know that their roles would reverse. If we were going to rotate around HT, then the cone would be spinning this way. And if we were to spin this way, then this would act as the height, and MH, 5 units long, would be acting as the radius. But just be mindful, we're spinning around MH. So now all we have to do is just plug this stuff in. We have volume equals 1/3 pi, and then we have 8 squared, and then times h is equal to 5. So now we can just type this all in the calculator. We have 1/3, so I'll just write 1/3 in parentheses, even though in this case it's not going to matter. It's just a good practice to get into. Now pi, we're going to press second and this up arrow here for the pi button. And then we're going to write in parentheses, we have 8 squared. And then we're multiplying all of this by 5. So I could just tack on times 5 at the end, or I could even just put another parentheses 5, because parentheses means multiply. And we're rounding this to the nearest tenth. So to the nearest tenth, this is going to be 335.1, because to the right of a 1 is a 0, so we round down to 335.1. So our solution here is the volume is equal to 335.1 cubic units. So here's our solution to 26. Question 27, we want to dilate triangle ABC using a scale factor of 2, and C is our center. So what I want to do first is extend the lengths of the sides of the triangle like this, and we're going to extend away from point C, since that's the center of dilation. And now that we've extended this, and we'll just adjust this a little bit so that it's perfect. So we're going to make sure this is as lined up as possible so that our dilation just looks as good as it could look. And what we're going to do is we're going to place the compass over here at C. We're going to extend and measure. First, we'll measure CA. And now we make a mark, and make sure you leave these construction marks on the page so that you get the full credit for the construction. And then you move it over to that arc you just made. And since we're using a scale factor of 2, we're essentially just doubling the length of CA by copying that same distance from A to this point on this dotted line here. And now we're going to repeat this process from C to B. So we're going to place the compass over here, and I have to adjust the length so that it matches the distance from C to B. And now I just swing an arc like this, and I'm going to move it over to that point of intersection, and I'm going to repeat this process so that we double the length of CB. So now we could label these points of intersection. So this one here we could call B prime, and over here we could call this one A prime. And if we want, we could also just call this point over here C prime as well, so that when we draw our triangle in a moment, all 3 vertices will have a prime. So now we just have to connect everything here. So we have from A prime to B prime, and now we connect from here to here, and we're connecting from here to here. And triangle A prime, B prime, C prime is the dilation of our original triangle by a scale factor of 2. Question 28, we have this wordy word problem, but this picture captures everything. So we have a rock climbing wall. The height of the wall is 5 meters, and there's a slanted section that begins 1.2 meters off the ground, and it comes out at an angle of 14 degrees. So now the actual question, we're going to determine to the nearest hundredth the length of the hypotenuse or the slanted section of this wall. So this is this piece over here, and let's use a color that actually pops out. So we're going to find this here. We're going to call it X, and that's our hypotenuse. So how do we know this is the hypotenuse? Well, we know it's the hypotenuse because it's across from the right angle over here in this section of the wall. So now we're going to go ahead and label some of the other sides. So this vertical side here is something that we can find, but for now we'll just call it Y. And the way we're going to solve for the value of Y is, notice this piece is 1.2. So if I go Y plus 1.2, that would cover the entire height, and the entire height they told us was 5 meters. But we'll leave the units out until the end. So now I'm just going to subtract 1.2 on both sides like this. And that tells me Y is equal to 3.8. So I'm going to replace Y, and just know here that Y is in terms of meters as well. So this is just going to be 3.8 meters. But now, moving on to the actual question here, we're going to have to choose a trig function. And the way we're going to choose a trig function, know this phrase, SOHCAHTOA. This helps you remember the ratios for sine, cosine, and tangent. And this angle was given to us over here, this 14-degree angle. And notice this side is adjacent to our 14-degree angle because it's right next to it. This side all the way up here is opposite because it's all the way across from the angle. Notice I have to go this entire distance across. So this would be the side opposite. So now the thought process here is I have this phrase jumping around in my head. I know the adjacent side, and I want to find the hypotenuse. So when I keep saying adjacent hypotenuse, that tells me to use cosine. So now I'm going to have cosine of, and the angle is 14 degrees, and adjacent to the 14-degree angle is the 3.8 meter side, and we're going to divide by the length of the hypotenuse is X. That's what we're looking for. And now I'm just going to call this cosine 14 over 1 so that we could cross multiply. And just note at the end, that's when I'll write our units in. So now we're going to have, in the next line, we have X times cosine of 14 degrees equals 3.8. And now we're just going to divide by cosine of 14 degrees to get X by itself. And now this is going to tell us here what we need to know, and what we need to know is what is the value of X. X equals, and now we just have to type this in. But one thing you have to be super careful of, notice it's cosine of 14 degrees, and right now the calculator says we're in radians. So we're going to press mode, we're going to scroll down over to degrees and press enter, and now we could just go ahead and divide. Little fraction trick, you could press alpha y equals enter, and that'll pull up a fraction like this if you have the TI 84 plus CE, and then we have 3.8 divided by, and we've got cosine of 14 degrees. And we're rounding to the nearest hundredth. So notice the hundredths place is a 1. We look to the right, it's a 6. So we're going to round this up to 3.92. So X equals 3.92 meters is our solution to this question. Question 29, we have right triangle BAL and altitude AD is drawn to hypotenuse BDL, and we're told the length of AD is 6. Now, this part we're told that DL is 4 times the length of BD. We want to determine and state the length of BD. So this is the actual question. So now if you think about this carefully, if BD is X, DL is 4 times the length of BD. So then this piece over here would be 4X. And now we have to think about what are we able to do with this information? Well, anytime you have a right triangle and the altitude is dropped down, we have 3 similar triangles. This small triangle, this medium triangle, and the big triangle are all similar, which means that their sides are in proportion. The corresponding sides are in proportion. So now what I would do for this is, it may be tricky if you don't know the altitude rule to see how to set the proportion up, but what you could do is you could take triangle BDA and you could redraw it like this. So I'm going to draw it like this. And I'm going to put the right angle here at vertex D. And this is going to be B, and this is going to be A. And notice BD is equal to X, and AD was 6 units long like this. So you see, I just kind of took this triangle here, and I pulled it out, and then I rotated it going in this direction like this, and then laid it down on side DA like this. And the reason that I did that is so that these two triangles now, this triangle that I'm highlighting in pink, you could see that it's facing the same direction as the red triangle. So now setting up the proportion should be a lot easier. So what I have here is that the vertical segment here, X over 6 in triangle BDA, is going to be equal to, in triangle ADL, that's going to be equal to 6 over 4x like this. Because once again, we're setting up the corresponding sides in our ratio. So we have the vertical side to the horizontal side, x over 6. That ratio has to be the same as the vertical side to the horizontal side, because the red and the pink triangle here are similar. So now we just have to do the algebra. We're going to cross multiply. We have 4x times x is 4x squared equals, and now we have 6 times 6 is 36. And then we could solve here by dividing both sides by 4. And now we're going to have x squared is equal to 9, and then we just take the square root of both sides. Now, technically the square root of x squared, so this is a subtle detail, is plus or minus x, or we could say the absolute value of x. But in this case, we're talking about geometry, and we're talking about the length of the side of a triangle. So here we could just say x equals 3. And now we have to think about, what are we actually trying to find? We're trying to find the length of BD. And notice that was modeled by x. So I could just say here that BD is 3 units long. So this is our solution to 29. Question 30 is a lot of pain and suffering just for 2 points. So we have a trapezoid. We have these two lines are parallel, AB and CD. And then we're told that diagonals are drawn. MN is drawn to intersect the diagonals at E. And we're told that AD is congruent to AE. So this triangle is isosceles. So then next what we have is the measure of the angles DAE is 35 degrees up here. And then the measure of angle DCE is 25 degrees. That's over here. And the measure of angle NEC is 30 degrees. And what we need to find is the measure of angle ABD. That's in this corner over here. So this angle here, which I'll just label with an X. So one of the theorems we're going to use a lot is that the sum of the 3 angles of a triangle equals 180 degrees. So we could use that a few times here. But another thing to note is, because this angle here is X and these lines are parallel, notice we have alternate interior angles here. So I could also label this with an X. So whatever happens first, I could either find this X or I could find this X, and I'm going to have my answer to the question. So one thing I notice here is we could use the exterior angles theorem, that we have a 30 degree angle plus a 25 degree angle telling us that this angle over here is 55 degrees. I could also add these two and subtract them from 180 to get this angle, but that's also going to tell me that this is 55 degrees. So the next thing we could find here is the measure of these base angles over here, because this is an isosceles triangle. Well, since this triangle is isosceles, we could say that these two angles are congruent. So if I have 35 degrees so far, we could subtract 35 from 180. And when we subtract, we're going to have 145. And since these two angles are the same, I could take 145 and I could divide it by 2. And that's going to give me 72.5. But over here, I'll write it with the degree symbol. On the side, when I do the arithmetic, I'm going to leave the degrees out just to save time. So now we have this one labeled, and we could use that to find some of the other missing sides here. Well, what we know about vertical angles is that vertical angles formed by intersecting lines are congruent. So this angle over here is also going to be 30 degrees. So now we have 72.5 plus 30, and we're missing one angle to make this straight line here. So what we're going to do is we're going to add these two angles together, and I'll start using the space over here. So we have 72.5 plus 30. That would give us 102.5. So if I want to find the measure of this angle over here, what we could do is we could subtract 102.5 from 180. And now I'm just going to put a decimal 0 so I could actually do the subtraction. So this is 7. I'm going to make this into a 10, but then I have to borrow and make this into a 9. And this is going to work out like this to 77.5. So now that I have the measure of this angle over here, this is 77.5 degrees. Now we just have to add these two angles and subtract them from 180 to get x, because these three angles have to make 180. So I'm going to do 77.5 plus 55, and I'll write a 0.0 here, is going to give us 0.5, 2, carry the 1, and that's going to give us a 13 like this. So what that tells us here is the sum of 77.5 and 55 is 132.5. So to get x, I'm going to do 180 minus the sum of those two angles like this. Okay, and if we do the long subtraction here, so I'm just going to borrow, make this a 9, this is going to be a 5, 10 minus 5, this is a 7, this is a 4. The measure of angle ABD is equal to 47.5, and now I'll tack on my degree symbol here. Now just note, if I had to check my answer to this, and we'll make this a little bit neater, what you could do is you could do 47.5 plus these other two angles, and they should add up to 180. Question 31, we're going to use this circle diagram here of circle O, and we're told the measure of the inscribed angle here is 36 degrees, and the length of OA, this piece over here, is 4 inches. Now notice that's the radius of the circle, because it goes from the center to a point on the circle like this. And now what we need to do is determine and state to the nearest tenth of a square inch the area of the shaded sector. So what we need to do to be able to find this area is we have to be able to find the measure of the central angle. So what we need to know is that the measure of the inscribed angle is equal to half the measure of the arc that it intercepts. So that tells us that this arc over here is going to be double this angle. So we have 36 degrees times 2 is 72 degrees. So that's the measure of this arc over here. And that tells us the measure of the central angle is 72 degrees like this, because the measure of a central angle is equal to the degree measure of the arc that it intercepts. So now we have enough information to answer this question. What we're going to do to find the area of just the shaded region, I just treat this as a proportion. Well, the total area of a circle is pi r squared. So here I'm going to say that the area of the shaded sector is pi times r radius is 4 inches, and that's being squared, but we're not finding the area of the entire circle. We're taking just this slice of the circle like this. So we're taking 72 degrees out of the entire 360 degrees that's available to us. Now notice the units just kind of cancel out like this, and now the rest is just calculator work. So we have pi second in this up arrow here, the caret button, and now next we're going to have 4 squared. So we have 4 to the second power like this. Now we close the parenthesis, and we're going to multiply by the fraction, and we're going to have alpha y equals enter. Or we could have just used parentheses, and we have 72 divided by 360 like this. So now to the nearest square tenth of an inch, this is going to be 10.1. So our answer to 31 is 10.1 square inches. So question 32, there's a little bit to read, but the picture captures everything that's given to us. And what we need to do is determine and state to the nearest meter the height of the tree. So what we're trying to find here is this distance here. And let's just say we call this y. We're trying to find out what is the length of y here, the height of the tree. So now what we could do is we could mark up this diagram, and we could focus on this right triangle here, the one I'm highlighting in red. And we could also focus on the right triangle that I'm going to highlight here in blue. So this bigger right triangle that kind of just encompasses everything to the bottom of the tree. Okay, so we're going to use 2 triangles here to answer this question. And both of these triangles are right triangles. And one thing that jumps out at me right away is if this building is 50 meters high, then this entire vertical distance I could also label as 50 meters. And then let's say I call this missing piece here, I call this one Z, and I call this horizontal distance X. So then if I were to extract these triangles here, let's say the triangle in red, I have this color coded. The triangle in red I'm going to draw like this. And this is a right angle, and the angle here is 13.3 degrees. The horizontal distance is X, and now this vertical distance here is just written as Z. So what we're going to do in this case here is look at the red triangle, and then the blue triangle is the big triangle. So that's the one that goes to the bottom of the tree. And that angle of depression is 22.2 degrees. This is a right angle. And now in this one, what we know is that the entire vertical distance is 50, and this one is X. So right now we know more information about the blue triangle. So that's the one we could start with. So what we could do with this one here is we have to think of SOHCAHTOA, and we want to know what X is. And right now X is adjacent to the angle that we know. And what we do know is the side opposite of the 22.2 degree angle. So that tells us we're going to use tangent, and we could say here that tangent of 22.2 degrees is equal to 50 over X. And now from here, what we're going to do is just a little bit of algebra. So we could cross multiply, and that's going to give us, we're going to have X times tangent of 22.2 degrees is equal to 50 times 1. So now we just divide both sides by tangent of 22.2 degrees. And this is going to tell us what the value of X is. And that's going to let us get to the next stage of the problem. So we'll just type this in here. We have 50 divided by, and we have tangent of 22.2 degrees. And just know for questions like this, I'd like to take a lot of the decimals. So this tells us here that the length of X, we have 122.5212599 meters. But now that we know what X is, we could take tangent of 13.3 degrees. So now we're focusing on the red triangle. And tangent of 13.3 degrees is going to be equal to Z over X. But we just found out what X is. So if we cross multiply here, we're going to have X times tangent of 13.3 degrees is equal to Z. So now we just do this answer here times tangent of 13.3. So now we could just press times, and we're going to write tangent of 13.3 degrees. And this is going to give us this value here. So we could just record the value of Z. We're going to have Z equals 28.9627, and then we have 9854. Now you may notice here that I'm not rounding just yet. They did say to the nearest meter, but just know I personally like to round at the very end, because what happens is if you round to the nearest whole number throughout the question, it could throw your final answer off by a little bit. So this is just something I like to be mindful of. So now that we just found the value of Z here, we're ready to solve for the height of the tree. And we could say here that the height of the tree, so we're going to write out our final answer. The height of the tree is equal to, and now we could round to the nearest whole number. So the entire vertical distance was 50 meters. And now we're just going to do 50 meters minus, and if we round this to the nearest meter, our Z value is 29 meters. So if we just think of the concept here, if Z is equal to 29 meters, then how many more meters do we need to make 50 meters? We're going to do 50 minus 29, and that's going to give us 21 meters. So this is our value for the height of the tree. Question 33, we want to prove that this quadrilateral is a rectangle. So the first thing we could do is graph this. Now, drawing this is not a part of your grade, but I highly recommend doing it because it helps you come up with the strategy for proving that height is a rectangle. Now, the strategy I want to use here is, first I want to prove that this is a parallelogram by showing that opposite sides, both pair of opposite sides are parallel. And we're going to do that by finding the slope of all four line segments. But the reason why I want to do that is once we know the slope of all four line segments, to prove that this parallelogram is a rectangle, we just have to show that we have one right angle. So we're going to show that one pair of these non-opposite sides here are perpendicular. So finding all four slopes is going to allow us to accomplish all that stuff. So let's go ahead and get moving here. So we have the slope of, let's say we do segment HY first. So the slope of segment HY, and just know the formula for slope, you do the difference in the Y values, like Y2 minus Y1 over X2 minus X1. So here, if we use that slope formula, we're going to do for hy, we have 9 minus 6 divided by, and we have 2 minus negative 3. Now this is going to give us 3/5. When we do 2 minus minus, it's going to become 2 plus 3. Now, one thing I look for right away is that when we're doing this, I know that the slope of PE has to be the same as the slope of HY or YH, because opposite sides of a rectangle are parallel. So if I get some slope other than 3/5, chances are I made a mistake somewhere. So that just tells me how to assess my work as I'm going. So now here I have the slope of PE, or I could say EP, either way. So the slope of segment EP equals, and we're going to do here, let's say we do -4 minus -1. So we have -4 minus -1, and then we're going to divide by 3 minus 8. So this now is going to give us, we're going to have -4 minus -1 becomes -4 plus 1. So we have -3 over, we're going to have -5. And this is going to simplify to 3/5. So right away, I'm noticing that these slopes match. So these two lines are parallel. And now I'm going to do the next round. Now we're going to find the slope of these two segments. So we have the slope of HE is equal to, and now I'm just using this formula all over again. So we have 6 minus -4 divided by, and now we have -3 minus 3. This is going to be 10 over -6, which reduces to -5/3. And notice these two slopes are negative reciprocals of each other, which would tell us that these lines are perpendicular. And if these lines are perpendicular, that means they form a right angle. So that's looking good for the proof. And now we have the slope of the last line here. We went from H to E. Now we're going to go from Y to P. So the slope of YP equals, and we have 9 minus -1 divided by, we have 2 minus 8. And this one here is going to simplify to 10 over -6, which also reduces to -5/3. So now we just have to summarize all this stuff. We could say that these two line segments are parallel because their slopes are equal. And we could say that these two line segments that I've indicated in red here are also parallel because their line segments or their slopes are equal. So now we've stated that both pairs of opposite sides are parallel. So now we could say here that HYPE is a parallelogram because both pair of opposite sides are parallel. Now to prove that this quadrilateral is a rectangle, all we need to prove here is that we have one right angle. So let's prove that H is a right angle. And the way we're going to do that is we're going to say here that HY is perpendicular to HE because these slopes are negative reciprocals of each other. So now that we've established that HY and HE are perpendicular, we could say that H is a right angle, and then that'll allow us to conclude here that HYPE is a rectangle because it's a parallelogram with the right angle. And just in case you've never seen this symbol before, the 3 dots in this triangular arrangement here mean therefore. Question 34, we have a packing box for baseballs. It's in the shape of a rectangular prism, and here are the dimensions. And we're told each baseball has a diameter of 2.94 inches. So we could assume these baseballs are spheres. And what we need to do for the first part is determine and state the maximum number of baseballs that could be packed in a box. And this part is really important. They're stacked in layers. Each layer contains an equal number of baseballs. So what I would do here is draw this out. So here's the rectangular prism, and there's a certain amount of planning that goes into these questions and details that you really have to look out for. So for this particular question, there's a few traps set right away, and one trap that's set here is that the dimensions are 2 feet by 1 feet by 18 inches. So notice the units don't match. So here I think about this really carefully. The ball is in inches, and if we look later in the question, the density is given in pounds per cubic inch. So it looks like they're committing more towards inches than feet. So that would tell me that I want to convert 2 feet and 1 feet to inches. Now, if you just know that 2 feet is 24 inches, then, great. But if you have to convert, you can multiply by 12 inches over 1 foot. And the units cancel here, and this is 24 inches. So that tells us we can label the length as 24 inches. And now going back, 1 foot is just 12 inches, and the height of this thing is 18 inches. So we have all three dimensions labeled here. Now the next trap that you could fall into, there's a lot of traps set here. The diameter of the ball is 2.94 inches. So the diameter, we need to use the radius when we start talking about volume later on. So the radius, we just divide this by 2, and we're going to get 1.47 inches. And the volume of a baseball is 4/3 pi r cubed, assuming that it's a perfect sphere. So the next dangerous trap here is what I've seen students do is they find the volume of the rectangular prism, they find the volume of one baseball using this formula, and then they divide them. But the reason why that's a very dangerous bear trap is the baseball is not made of liquid. That means when we drop the baseballs in, they're not going to melt and fill in all the space. When we start stacking these baseballs and we line them up like this, notice there is space between the baseballs. So this is not going to be a nice, smooth, every space is filled type situation. There's going to be gaps here. So we have to approach this a little bit different here. So what we're going to do is we're going to take the length, 24, and it's 24 inches, but we could leave the units out for this part. So 24, and we're going to divide by the diameter of the baseball, because you can see here, as we start stacking these baseballs, we're kind of just like lining up all these diameters here. So we're going to have 24 divided by 2.94, and that's going to tell us how many we could fit going across. And we're going to repeat that for the other dimensions. So let's do all three division problems. We have 24 divided by 2.94, and then that's going to give us this value here. We have 12 divided by 2.94. So that's our width. And then the last one here, we're going to divide the height, 18 inches divided by 2.94. And that's going to give us this value here. So now we'll record these all. We have 8.16, and this goes on. But let's think about this very carefully. We can't have 0.16 of a baseball. We're not going to cut these baseballs and have a fraction of them. So we could fit 8 going across. Okay, so there's 8 that could fit going across. Now we could see how many could we fit going backwards here. So when we took 12 and divided by 2.94, this worked out to 4.08, and this continued, so we could fit 4 going back. And now we want to see how many could we fit going up. So that's the 18 divided by 2.94, and that works out to 6.12, and this goes on. So we could fit 6 going up. So now to find the max number of baseballs, so we have the max, so let's just make that a little bit neater. The maximum number of baseballs is equal to, we're just going to multiply these three values together here. We're going to do 8 times 4 times 6. So there we have it. We could fit 192 baseballs inside this rectangular prism. For the last part here, we're told the density of the baseballs in pounds per cubic inch, and we need to determine and state to the nearest pound the total weight of all the baseballs in the fully packed box. So because there's a unit of cubic inches here, what we need to do is find the volume of all the baseballs. So we could see here that the total volume of baseballs, so the total volume of the baseballs is going to be 192 times. Since there's 192 baseballs, we're going to multiply 192 by the volume of one baseball. And the volume of one baseball is 4/3 pi. And then we have the radius being cubed here. And the radius, remember, was 1.47 inches. Now, I'm only including the units here, even though this is not necessarily part of the score. But I like to include the units so that we could see how the units cancel at the end and give us our answer in pounds. So now let's just multiply this out. We have 192, and now we're multiplying by 4/3. So I'll just put this part in parentheses. And then we have pi is second and this up arrow here. And then we have 1.47 to the third power. So I have 1.47, and now I hit this up arrow to the third. I could have wrote the 3 outside the parentheses, but this is also okay. And that's going to give us this value here. So the total volume is equal to 2554, and we have 0.711378, and the units are inches to the third, or we say cubic inches. But now we're almost done with this question here. The last thing we have to find here is the total weight. And to find the total weight, what we're going to do is we're going to take the total volume in cubic inches and multiply by the density here. And the reason why we're multiplying, if we write this out, So this was our answer to the previous stage of the problem, cubic inches. If we multiply by 0.025 and the units here for the density is pounds per cubic inch, notice that inches cubed over inches cubed cancels, and this is going to give us the total weight after we multiply these. So now we could just press times and we have 0.025. So the total weight to the nearest pound is 64 pounds. So we round at the very end here, we have 64 pounds. That is the total weight of all of the baseballs. So question 35, the final boss, we have the 6-point triangle proof, and we have all this given information here, and this is what we want to prove, that EH times CH is equal to the product of, we have FH times AH. So anytime we have the product of segments are equal, that's shouting out similar triangles because of that statement reason where we have the products are equal because the product of the means is equal to the product of the extremes. And since these two triangles are involved with these four segments, that's going to build our strategy here. So our strategy is going to be to show that triangle AHE is similar to, we would have triangle CHF. And notice I wrote the letters in corresponding order. A and C are congruent angles. H over here, this vertex, these two angles are the same because they're vertical angles. And then angle F and angle E over here are going to be congruent as well. So the lettering is very important. And notice I wrote the givens right away. There's nothing exciting about that because the givens is just given to you and you get no points for doing this. But now what I'd like to do after I have my strategy is I'd like to translate the information that was given to us over to the picture. So we have EF is parallel to AD. So if we just draw that in, we could draw arrows here like this, that these two segments are parallel. We're also told that EF is parallel to BC. So right away, I can see that AD and BC are parallel. So this is looking like a parallelogram. And now we're told AD and BC are congruent. So if I mark this off, notice we have one pair of opposite sides are both parallel and congruent. So that tells us right away that this is a parallelogram. But we have to be sure that we state everything. At no point did we say that AD is parallel to BC. So this is going to be our first statement. We're going to say that segment AD is parallel to segment BC. And the reason being that they're both parallel to a common side. So we could say all that two lines that are parallel to the same side are parallel, or we could just say the transitive property. So if you forgot that one, just know the transitive property does apply to parallel lines, that we say if A is equal to B and B is equal to C, then this implies here that A is equal to C. So that's for transitive property of equality, but it also applies to parallel lines here. So now that we've stated that the opposite sides of the quadrilateral are parallel, we've already established that the opposite sides here, AD and BC, are congruent. So now we could state that ABCD is a parallelogram because it has one pair of opposite sides that are both parallel and congruent. So now to prove that these two triangles are similar, I want to target these angles over here. I want to target this angle and this angle, which I'm labeling with a 1 and a 2. And the reason I'm labeling it is so that I don't have to write 3 letters when I write it over here in the proof. So one thing we have to be careful with is that to use these two angles as alternate interior angles, we have to first state that these lines are parallel, AB and CD. Now, we may think that's obvious because this is a parallelogram, but at no point did we state that these lines were parallel. And if you're going to use alternate interior angles, the lines that build the alternate interior angles have to be parallel. So we have to make sure we state that. So now that we've established that these lines are parallel, we could state that angle 1 and angle 2 are congruent. Okay, I noticed that our reason for 5 that I have a lot of abbreviations here. For parallel, you could just put these two vertical lines here. Angles, I just have kind of looks like a less than symbol, and then are congruent, I just put the symbol for congruent. So now for the next stage of this, we're going to prove that these angles here, angles 3 and 4, are congruent. And the way that we know this is that these are vertical angles. So for statement 6, we have angle 3 is congruent to angle 4, and our reason is that vertical angles are congruent. So now that we have our two pairs of angles are congruent, now we could say here that the two triangles that we talked about in our strategy, triangle AHE is similar to triangle CHF, and this is because of angle-angle similarity. So now we could set up a proportion involving the four sides in our similar triangle. So we could say here that EH over, let's say, AH is equal to, so this is the short side over the long side, that's going to be equal to the short side FH over the long side here, which is CH. And now if we just look here, notice that when we cross multiply, that this is going to give us what we're trying to prove here. So this is a good start. But how do we know this is true? Because corresponding sides of similar triangles are in proportion. And now we could finally write out our proof statement here. We could say here that for statement 9 that EH, this segment, times CH is equal to, we have FH times AH. And the reason being that the product of the means is equal to the product of the extremes.